Now, earlier we talked about all of these different computers, like the integrated circuits computers and then the microcomputers which hosted this and etc. When we talk about the computer being able to compute, actually what happens is that they'll go through this cycle called the machine cycle. Right? This is where they will take things from the memory called fetching, and then they'll translate this called decoding. Right? Then they will calculate it, right? It's called execution or execute, and then they'll write it back, put it back to memory. That's called store or write back. Store, otherwise called write back. Right. Okay, let's see what this means. Let's say, for example, you're working on Microsoft Word or something. Hopefully you still remember this diagram from the first week, right? We have, the storage lah. We have RAM here and CPU here, and then input and output. Okay, so what happens is that each and every one of the software that is currently being used will be loaded inside your random access memory. It's like the workspace for the software currently in use. So once it is loaded there, it's like it is taken center stage now. Meaning, when you do something with your input device, your computer will respond depending on the kind of software which is inside RAM. So to be able to know what kind of output to give to the user, the CPU will fetch the next instruction from the software, right? So the software will say, okay, this guy just typed in A, right? And when he or she typed in A, there is a lot of things that you need to be taken into consideration, even if it's just Microsoft Word. For example, A needs to be displayed, and what kind of font and font color and lots of different things, right? So that instruction will be in RAM. It's like there's a list of instructions. You just imagine there's a list of instructions. Instruction 1, 2, 3, right? So these are all from Microsoft Word. It will tell the CPU how to calculate before you give it back to me, before I can give it to an output device. Okay, now the CPU will then fetch the next instruction from memory, right? So the diagram will look something like this, right? So this is memory, this is control unit, this is arithmetic logic unit, right? So this is the CPU execution cycle, right? And this is the memory. So the control unit will fetch from memory, right? So fetch it, take it, right? And then the control unit will decode. You see, all of these programs, they have their own language, whereas the CPU is sort of talks using its own language. So the control unit, right? Control unit. Control unit will translate so that it can then be calculated in the arithmetic logic unit. Arithmetic logic unit. So first the control unit will fetch from memory and then decode or translate and then give it to arithmetic logic unit. Hopefully by looking at this arithmetic word, it actually means simple maths, plus, minus, multiplication, division. That is arithmetic and basic maths, so to speak. Right? So you take it, arithmetic logic unit will execute, that means calculate, and then give it back to memory. Or rather, the control unit will take it from arithmetic logic unit and give it back or store to memory or write back to memory, right? So it begins here, fetch, decode, execute, and store. And that is the machine cycle. And that happens for each and every one of the instructions. Every time you say something to the software which is being loaded to RAM, this will happen. Right? Okay, needless to say, this is the CPU, right? The whole thing, control unit, arithmetic logic unit is CPU. This is memory. Now, while this is happening, sometimes calculations are complicated, right? And when calculations are complicated, the ALU, while doing calculations, need to store the value of calculations somewhere first before it can give back to memory. It's like, for example, let's say, for example, you are calculating the square root of something. Now, you imagine calculation of square root involves some kind of arithmetic logic operation that you need to do repeatedly, somewhat, right? So in order to do that, once you get some kind of a result, this is a result, but cannot write back, cannot store yet. Meaning you cannot give this to memory yet, because the calculation is still not yet done. You still need to do some more calculation. So you put this inside the register, right? So the register is also something which is inside the CPU. So the CPU has three parts. The first is control unit, the second is arithmetic logic unit, and then the third one is register, which will keep things as the arithmetic logic unit is doing the execution, right? So please remember, the machine cycle is done by the CPU, right, in connection with the memory. First part is fetch from memory, second part is decode or translate, then it gets calculated. If it's a complicated calculation, it might get stored to register, right, interchangeable with register, after which it will get stored or written back to memory. And that is the machine cycle, and that is the work of the CPU, which is before we have the microprocessor that we have nowadays. This whole thing is actually done by a whole computer, which is the size of a file cabinet, right? That is how amazing the computer you have in your back pocket is. You can do all of these things. We have just learned about the machine cycle, which consists of fetch, decode, execute, and store. Right? So one by one by one. Okay, so this goes here. So I'm writing it using acronyms now, F, D, E, and S, F, D, E, and S. And of course, you know, when you buy CPU, there are different prices for different kinds of CPU. So, for example, we have Intel and AMD, different branding. And then Intel CPU also, we have different kinds of pricing. We have Intel Xeon or Celeron or Atom. Different kinds of materials will fetch different prices. And in reality, central processing units are not created equal, meaning there are different kinds which will then fetch different prices. For example, one thing I would like to discuss right now is the use of pipelining. Pipelining, what is that? That is where you use some kind of technology where the resources that you use for fetching, decoding, executing, and storing can multitask and can multitask, and so more things can be done at one point, right, and at the same amount of time, right? For example, we compare these two CPUs. The first one here does not have pipelining, right? CPU number 1, no pipelining. CPU number 2, pipelining. And without pipelining, what happens is that, let's say all of these steps in the machine cycle will take 1 second each, 1 second, 1 second, 1 second, and 1 second. So what happens here is that to finish task number 1, we'll need 4 seconds. Then task number 2 will get in at second number 5, right? After 4 seconds, 5, 6, 7, 8, 2 tasks is out. You know, let's try it now. So 1, 2, 3, 4, right? 5 seconds, 6, 7, and 8. Right? So task number 2 will get out at 8 seconds. This is without pipelining. With pipelining, on the other hand, right? Second number 1, task 1 will get in, will be fetched. This is second number 1, right? At the second, as task number 1 gets decoded, task number 2 will get in. Right? So this is only the second. Right? As task number 1 gets executed, which is the third second, task number 2 will get decoded. This is the third second, and task number 3 can get in, fetched. This is the third second, and so on and so forth. So I'll erase this first. This is CPU number 2, right, which uses pipelining. So this carries on forward as we go to task number, as we get to second number 4, right, here and here and here, 4, right? 4 and 4. And needless to say, as we get to 4, 5, 6, 7, after 8 seconds, all 4 tasks will be done. Right, so I can just put this here, 4, and then 5 here, and then 6 here, and then 7 here. And then after 7 seconds, all tasks will be done, right, as we go along. Meaning as soon as the resource is free, right, here second number 3, this resource will be free then because it has already moved there. Now this task will get in. That is pipelining. You can refer to your slides. The diagram might be clearer there rather than this one. I'm not sure which will help you understand better. But basically here, after 8 seconds, or rather at the 8th second, only 2 tasks would have been done, or at the final stage of getting done. Whereas here, 8 seconds, all 4 tasks are done. And so this is called pipelining. And this is one of the factors that affect the performance of the CPU. We have other factors as well. Right? For example, we have the amount of transistors. Right? Although this looks simple, meaning it's just diagrams and we can't really imagine what's happening inside the computer and stuff, what happens is that you will need a lot of transistors to be able to do this, to be able to like say, you know what, okay, you know, it's like people are lining up and you like rearrange them. Okay, you go here, you go there, you know, you're done with your task, go somewhere else. It's like, you imagine you're preparing a meal for someone. Let's say it's a rojak meal, right? So rojak will have like 3 or 4 counters. Let's say we have the veggies, right? We have the fried stuffs, right? And then we have the gravy, and let's say we have, okay, before gravy, let's say we have some kind of like a sotong, cuttlefish, right? Squids, and then gravy. Okay, so you can be like a gourmet rojak where first veggie and then fried stuff and then squid and then gravy, then you give it to your customer, then you prepare the second one. Or you can have 4 people working at these different tables, and once you're done with one task, you pass it to the next table, you can immediately begin the next task, right? So pretty much like that, right? So to be able to do that, you need to have the resources, and that resource is transistors, right? So whether or not you can do pipelining, you need a lot of transistors. So this will affect the performance of your central processing unit. Other than that, we have the clock speed, right? You know that your processor will, you will see, like for example 2.6 gigahertz or 3.3 gigahertz, and this is what we call the clock speed, right? Needless to say, the higher this number, the faster the performance of the processor or CPU, right? So this affects processor performance as well. The clock speed, number of transistors, right? Whether or not the processor applies pipelining, right? Other than that, we have this concept called parallel processing. You see, computing has become so advanced nowadays that there are certain motherboards which can have more than one CPU, right? You see, you can have, like for example, two CPUs, 1 and 2, right? So when it has two CPUs, basically if you have one task like this, it can be divided into several CPUs and calculated simultaneously, right? So parallel processing will look something like that, right? So one task gets processed by different CPUs, and that is called parallel processing. So if your motherboard is capable of parallel processing, that will affect CPU performance as well, right? Then aside from this, you might have also heard of things like dual core and quad core, right? Dual, quad, right? Dual means 2 times, quad means 4 times the core of the processor, meaning it's like you have one processor with, it's like a twin of processor inside. You only have one processor which you put on your motherboard, but on the processor itself, instead of buying an expensive motherboard that can accommodate several processors, you buy a regular motherboard, but this processor itself is actually 2 processor in one kind of thing. This is dual core, or 4 processors in one. And I've heard and seen smartphones with like octa-core, 8 processors in one, right? So this also improves performance, parallel processing as well as multi-core processing, right? So amount of transistors, clock speed, parallel processing, multi-core processing, whether or not your processor can do pipelining, right? As well, there are certain other things. I think okay, if I just erase this, hopefully you get that in memory already. Sorry for having such a small whiteboard, right? But again, these things are available in your slides. You can refer there, right? So we also have things such as the word size. You'll notice that, for example, Windows 7 and Windows Vista, they will have 32 bits or 64 bits, right? So this will affect processor performance, meaning to say that if your processor can do operations 32 bits in one go, one cycle is 32 bits, then this is to say that more things can be processed at once compared to 16 bits or 8 bits. If it's 64 bits, then more can be processed at once as compared to 32 bits, right? So the higher this number, that means more can be done. So for example, 32 bits, maybe you can have awesome games. 64 bits, you can have awesomer games, like for example 3D games or something, and 3D sounding games and whatnot, for example. And then we also have, this is called word size, right? This is the size of the word. It's like, you know, earlier we talked about 8 bits being 1 byte and stuff. So these processors, they consider their word as being 32 and 64 bits respectively, right? For example, 64 is better than 32 and etc. Faster, supposedly more things can be done and processed. Then we have operations per clock cycle. So this is how efficient the processor is, meaning to say that it has to do something to do with the design, and transistors. Meaning to say that whether or not you have the people to do the work, and whether or not the people that does the work actually knows how to do it. It's like they receive proper instructions, right? So this is operations per cycle, and this also affect performance of processor. And needless to say, we also rely on materials, meaning what did you use to build the processor, right? We have cheaper processors like Celeron or Atom, and then we have more expensive ones like Pentium and Xeon. These are more expensive processors using more expensive semiconductor materials, so they tend to perform better, and so they are more expensive, right? And so these are factors that affect the performance of a microprocessor.